So in my previous class, we have already discussed about few terms related to quadratic residues. So in my class, I will continue it and I will show a few of the interesting applications of this quadratic residues and quadratic non-residues. Okay, so if we go back, so what are the applications? So most of the applications of quadratic residues are basically the primality testing. For example, I have already shown you in my last class that how to get this big prime, or is it really possible for a small laptop to get these big primes? And in our public key crypto system or in most of the cryptographic schemes, we have already shown that these big primes are very important and they actually provide us a lot of security in terms of digital security. So to achieve this kind of securities, we read basically this big prime. So the question is, how did I get this big prime? In my class, I will basically show how to apply the law of quadratic residues or the quadratic reciprocities to get these big primes. So few terms already we have described. The first term is what is quadratic residues. So if we go back little, then we defined the quadratic residues in terms of normal group. So if G is a group, then an element A belongs to G is said to be a quadratic residue if there exists some element X belongs to G such that X square equal to A. Okay, so that's a more general definition of quadratic residues. But if we consider a particular case, for example, if we consider Z to be Zn plus, so we know that this is a commutative, finite, and cyclic group. And if we consider G to be my Zn plus, then an element, a class A belongs to Zn is said to be a quadratic residue modulo n if we put some definition condition GCD of an equal to 1 and there exists some class X belongs to Zn such that X square equal to class A. So that's the same definition. So here these are the elements of the group, the same thing as this. So then we called class A is said to be a quadratic residue modulo n. So in general, we say that an element A belongs to Z is said to be a quadratic residue. Usually the positive integers z a belongs to Z is said to be a quadratic residue if quadratic residue modulo n if GCD of an equal to 1 and the equation x square congruent to a modulo n has a solution in Z. That means it should have some integer solution. Okay, then we say that A is a quadratic residue modulo n. So this we have already seen, and if we go for some example, then if we have seen that if we consider Z11 star, that means group of all units of Z11, that is U11, then with respect to that we have shown that there are exactly 5 elements which has quadratic residues and there exist exactly 5 elements which are quadratic non-residue. For example, if we consider 1 square, then it's 1. If we consider 2 square, then it's 4. If we consider 3 square, then it's 9. If we consider 4 square, then it becomes 16. 16 means 5. If we consider 5 square, then it's 25. That means class 3. Similarly, if we consider 6 square, this becomes 3. Then if 7 square, 8 square, 9 square, and 10 square. Okay. So these elements are basically quadratic residues because if we consider 1, then we see that 1 square or 10 square equal to 1. So they are the quadratic residues, QR. and you see that there are other elements, for example, class 2, class 6, class 7, class 8, and class who left 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, so 10 is left. So exactly 5 elements are there from Z11 star, which does not have a square root. That means they are quadratic non-residues. So they are quadratic non-residues. So as I mentioned in my last class, there are exactly half of the elements of GFD11 star are quadratic residues and half of the elements are quadratic non-residues. So the question is it true for any odd prime? And the answer is of course yes. In my last class, I have already shown in ZP star where P is a odd prime, then there exist exactly P minus 1 by too many quadratic residues and exactly P minus 1 by too many quadratic non-residues where P is a odd prime. So that's quite interesting result. So the question is, if I ask you a simple question that can you see, if I give you two elements, can you quickly give me the answer that whether they are quadratic residues or not? For example, if I ask you the question like, if I give you say, uh, if I give you say 90, say 7, and if I ask you whether 97 is a quadratic residue modulo 101, then we may be stuck. So how to find? Do we really check all the elements of jet 101 star to check whether 97 is quadratic residue or non-residue? So, so the question, so this is a question, how to answer this? So to answer this question, we have shown in my last class that we use a technique called Ligendre symbol. So what is that Ligendre symbol? If P is a odd prime, so this is odd prime, and if we consider this to be say A is a positive integer such that GCD of AP is 1, then this is Legendre symbol AP. This value, it takes two values. One, if A is a quadratic residue modulo P, and minus 1 if A is a quadratic non-residue modulo P. Now, till now, even if we can define this Legendre symbol, we are not in a position to exactly give you some of the hints how to uh, compute or how to compute this AP. So for that, in my last class, I have given you a bunch of formulae that actually helps us in finding whether a number, whether how to calculate this Legendre symbol. So few of them are as follows. So if we look at uh, this is quite interesting. So Legendre symbol AP, this is nothing but a to the power p minus 1 by 2 modulo p. So in my last class, I have already proved this by using the generator, because we know that if P is a prime, then ZP star is a cyclic group. So if this is a cyclic group, then there must exist some generator. And if we have a generator, then we can express every element of ZP star in terms of the generator. And based on that, we can find these values of AP, the Legendre symbol AP. So we have seen that this Gn is, if g to the power n is a quadratic residue if n is even, and g to the power n is a quadratic residue if n is odd. And based on that, this theorem or this result can be proved very easily. So this is very handy thing to calculate. For example, when I ask you this, so basically I am asking you the question, what is the value of 9701? Okay, what is this value? Now can somebody be able to tell me what is this value? Legendre symbol 9701. Can somebody Help me
Sir,
in
it is 1.
why
It is
this
a
is
quadratic.
1.
Sir, I calculated this.
Okay, how do you calculate this?
Sir, since 101 modulo 4 is 1, so we
Yes.
can replace it by 101.97, and 101.97 is equal to 497, and 497 is nothing but
So first thing, whether
297.
97 is a prime or not?
Yes, sir, prime.
Yes. So it's a
So
prime,
2,
and then
2,
based on
2
the
square
law of
and
quadratic residues, you did it, right? Okay. Yes,
yes,
very good. So the first thing that with this formula that we have just now, if we have want to calculate with this formula, then what how it looks like? It should be A. So here this is our A. So that should be 97 to the power 101 minus 1 by 2 modulo 101. Okay. So if I have this, then this is nothing but 97 to the power 50 modulo 101. Okay. So again, this 97 to the power 50 modulo 101, calculating this is not a very easy task. So that would be very difficult for us to directly calculate 97 to the power 50 modulo 101. So this way, with this formula, we may not be able to go further. Okay, let us have some more formula that may help us in finding these values. Okay, so if we go little beyond, then let's see what happens. So there are few handy formulae that would be helpful for reducing further. So for example, this is AB mod P, Legendre symbol P is same as AP BP. Note that both A and B, they both of them are relatively prime with P, and where P is a odd prime. Similarly, if A mod P, this is very handy formula, so that would be useful in many places. So if A congruent to B mod P, then suddenly A P equal to BP. Also, if I by any chance if we have some a square form, then this value will always be 1, and 1p is 1, minus 1p is the formula like this. AP is minus 1 to the power p minus 1 by 2, and this is sometimes also very important, 2p equal to minus 1 to the power p square minus 1 by 8. So they are few important formulae, and we have already shown this result in my previous class, and based on this results, this except for this is little tricky. So if someone wants to prove the wants to read the proof of this result, may go to my book, and in chapter 10 we have a detailed proof. It's not that difficult, but it has actually 4 cases to prove this. There may be other ways to solve also, but this proofs remaining from this, we have already shown in my last class this proof, and based on this proof you can see very easily that how this proofs follows. For example, if you want to do that, so APBP, so this is AB whole to the AB Legendre symbol P is same as AB to the power P minus 1 by 2 modulo P, and then you can break it like this. So we can do like this, like, so ABP is same as AB to the power P minus 1 by 2 modulo P, and this is same as a to the power p minus 1 by 2 modulo p into b to the power p minus 1 modulo p, and that is same as ap bp. So this is in terms of modulo, and then as I mentioned in my last class, 3 extra steps will give you the equality. So now it's in modulo p, but 3 extra steps, like what could be this value, AP and BP, these values could be either 1 or minus 1. Based on that, you can reduce that, the equality holds. Okay. Similarly, these results are also very easy. So you can just substitute here, and then you will get this value. So a square p, so how to prove this a square p? So this is also very easy to prove. So a square So a square p. So you don't need to prove anything. So as I mentioned, so you just put it here. So a to the power a square to the power p minus 1 by 2 modulo p. So this is nothing but a to the power p minus 1 modulo p, right? And since GCD of A and P are 1, by Fermat's last little theorem, you can say that this is nothing but 1 modulo P. And again, by 3 extra steps, you can readily prove that A square P is exactly equal to 1. Okay. So you are done basically. Uh, Also, you can easily use this one. See, A square other way around. So a square p, it might have a easier method to solve this. AP BP, sorry, AP, and this value is either 1 or minus 1, or this value is again 1 or minus 1. So that means is nothing but minus 1, sorry, plus minus 1 whole square. Or you can say that this is nothing but AP whole square. Now this value AP value is either 1 or minus 1. So as a result, the whole thing value will be 1. So there are plenty of proofs of doing the same thing. And similarly, you can just put this value here for this. You can just apply this formulae, then you are done basically. And for this one, it's a little bit three to four extra cases will come. How the form of this P will look like. The form of P might be in terms of 8. So any odd prime P must look like of this form. So any odd prime P must look like some 8k plus 1 form, or 8k plus 3 form, or 8k plus 5, or 8k plus 7. So any P which is odd must look like any one of them. Okay. And based on that, we will have this proof technique. So if somebody wants to have a look at this proof, he or she must look at my book or any number theoretic book, that they will find this easy proof of this. So I'm not going to the details of this proof. Okay. But most importantly, this law of quadratic reciprocity is playing the most important role. So while calculating this, this is very important and essential. So here, what is that says, if P and Q are two distinct odd primes, note that they should be distinct odd primes, then this value PQ and QP is nothing but minus 1 to the power P minus 1 by 2 into Q minus 1 by 2. That means, or it can be reduced, simplified in that way, the value of PQ is same as, just I have reversed it, it is QP. Okay, I have just altered QP, and this value will be the same if any one of this P or Q is of the form 1 4k plus 1 form. If this is 4k plus 1 form, at least one of the P or Q, then the value will be the same. But if both of them are of the form 3k plus 4 form, both P and Q are of the form 3k plus 4, then this value will be the exactly opposite of that. Okay. Now, as I mentioned, my question was, what is the value of 9701? As somebody told that this is a prime and this is a prime, both of them are odd primes. So just check whether some of them are of the form 4k plus 1. So this is a 4k plus 1. So this same as 101 divided by 97, not divided by. So Ligendre symbol 10197 modulo 97. Now apply this result. Say A is congruent to B, then what is this value? So A congruent to B. So here 101 and 97 modulo 97. So let's check. So 101 congruent to how much modulo 97? So somebody tell me, it was 4, right? So 4 plus 97. So that means this is same as 4 by 97, Legendre symbol. Now since this is of the form 2 square 97, so you don't need to calculate anything else. This value will be 1. So the question that I asked whether 97 is a quadratic residue modulo 101, the value is right because the value is 1. That means 97 is a quadratic residue modulo 101. So we are done. So this results, all the formulae that I have used here playing an important role, but the most important role that is giving us is the law of quadratic residues, which says that how to reduce this, how to convert a bigger number into a smaller number. So you just make it like this and then use this formulae to reduce this, and then you can very easily calculate a bigger number, which was initially we thought that 97 to the power 50 modulo 101 that we needed to calculate. But now it's very simple. Within 3 or 4 lines we got the answer. So that's the way that one can solve this. Okay, now let me ask you the question, how do you then use it in terms of primality testing? That means how to check whether a number is prime or not. So there it plays an important role. So this result will be playing an important role. What it says, if P is a odd prime and A and B, so here only A are used, so B is not required. So if P is an odd prime, then AP, Legendre symbol, must be equal to this. So that means if P is a odd prime, that will give me the result that P odd prime will imply Legendre symbol AP congruent to a to the power p minus 1 by 2 modulo p. So where a GCD of AP equal to 1. So if I choose any a, and if p is an odd prime, then suddenly that will imply this value equal to 1. Now tell me in terms of logical sense, if a is congruent to b modulo p, okay, not a congruent to, say a, some statement a implies b, what is the equivalent logical statement in terms of negation? Can somebody tell me this answer? A implies b, what would be the logical equivalent statement in terms of negation? So what can you tell about negation A, negation B? Any relation that one can tell? Somebody?
So
Very often.
negation of B is implies negation of A.
Exactly. So that is negation of B implies negation of A. So this is the logic very frequently we use in mathematics. But sometimes I found many students, while they use some logical reasoning, sometimes they use this term, negation A implies negation B. But this is highly wrong. So you have to remember A implies B is logically equivalent to, it just opposite, negation B implies negation A. So this is not correct. But unfortunately, some of the students I have seen in some of the logical ideas, they use this kind of concept. As a result, their whole concept become wrong. Okay, so that is a result where we are going to use in case of primality testing. But since here we have p is prime, so I need to take some composite number as well. So we cannot deal with prime numbers in case of only primality testing. So we should have something more. Before going to that, so that is known as Jacobi symbol. But before going to that, let me explain little more results related to quadratic residues. Okay, so let me check. Yes, so we can have, this is from my book. Maybe one can have a look at this results. So this part, the proof I have not gone, but there is an important result that is known as Gauss lemma. So Gauss lemma is very interesting, and sometimes that also helps us in calculating the Legendre symbol. So I have given you few of the techniques how to calculate Legendre symbols, but there is another technique which is very much useful sometimes, that is known as Gauss lemma. Okay, so to explain this, let me explain in this way through an example. Let me explain. Okay, suppose I want to calculate say 513. Okay, so Legendre symbol 513. So by using law of quadratic reciprocity, now it's very easy for you how to calculate quadratic reciprocity. So we know that 5 is 1 mod 4, so this value should be same as 13.5, and 13.5 is same as 3.5, and 3.5 is same as, so you can say this 3 to the power 5 minus 1 by 2, that means 3 square modulo 5, that means this is nothing but 9, that means minus 1. So it's very easy to calculate by using law of quadratic reciprocity. But Gauss also, you can understand, Gauss was also a very great mathematician. He also gave another technique which is known as Gauss lemma, and that technique is sometimes very much useful to prove many of the results, especially to prove the law of quadratic reciprocity. So here we have directly used the law of quadratic reciprocity. But to prove the law of quadratic reciprocity, Gauss lemma was very important. And there is a very interesting history behind the proof of this law of quadratic reciprocity. I will come to that. But before that, let me explain what is the this Gauss lemma. Okay. So Gauss lemma is basically is used to calculate some Legendre symbols, say AP, where P is odd prime and A is an positive integer or some integer which is relatively prime to P. What Gauss says that okay, you have A, then consider A, 2A, 3A till P minus 1 by 2A. For example, if we have 5, 13, then A is your 5, then go to 5, 2A means 10, 3A means 15, 20. So what is P minus 1 by 2 is 6. That means 25 and 30. So here this is A, this is 2A, this is 3A, 4A, 5A, and then 6A. Okay, because here P minus 1 by 2 is 6. Then from here, just take the modulo of this value, modulo n or modulo P. So 5 modulo 13 is 5, 10 modulo 5 is 10, but 15 modulo 5, that becomes 2. So 15 modulo 13 becomes 2. 20 modulo 13 becomes 7. 25 modulo 13 becomes 12. And 30 modulo 13 becomes 26, 4. Okay. So consider this set. So this is basically you are taking A to A dot dot P minus 1 by 2A, then convert all these A to A P minus 1 by A into the least modulo P. Okay. So this is the least value modulo P. Now find how many of them reduced values are exactly greater than P by 2. How many of them are exactly greater than P by 2? So here P is 13. So P by 2 is 6.5. That means how many of them are greater than, strictly greater than 6.5? See, so this is the value which is greater than 6.5. This is strictly greater than 6.5. This is strictly greater than 6.5. And Gauss called that number as mu. So here the value of mu is 3. Okay, and Gauss mentioned that the value of this Legendre symbol AP will be minus 1 to the power mu. That means minus 1. So just now we have calculated this by using the law of quadratic reciprocity, and we found that this value was exactly minus 1. And Gauss also gave one technique how to solve this, and that technique was by Gauss lemma, and there also we found the same value, this minus 1. So is the idea clear, or shall I repeat once again? Is the idea clear to all of you? Okay.
Yes.
So let me go to the statement then. So from the statement, it will be even clearer. So the Gauss lemma states that let P be an odd prime and A be an integer such that GCD of AP equal to 1. Okay, that's required for our calculating Legendre symbol. To calculate Legendre symbol, P has to be odd prime and GCD AP should be 1. Then consider A, 2A, 3A dot dot P minus 1 by 2A and their least non-negative residue modulo P. So their least non-negative residues modulo P means we have A, 2A up to P minus 1 by 2A, then convert it into its least non-negative modulo P. That means 5 is becomes 5, 10 becomes 10, but 15 becomes 2. 20 becomes 7, 25 becomes 12, 30 becomes 4. So consider this set. So that's what it says, that consider and their least non-negative residues modulo P that exceeds, okay, then consider their least non-negative this, and then calculate the number which are which exceeds p by 2. That means consider the integers this and their least non-negative residue modulo p that exceeds p by 2. So here we consider these three values which exceeds p by 2 means 6.5. Let mu denote the number of these residues modulo p that exceeds p by 2. Then AP is nothing but minus 1 to the power mu. Okay. So if somebody wants to have a look at the proof of this result, then the proof is not very difficult. So they may go to this. So it's a simple argument. So it's already given in my book at page number, PDF page number 435. So if somebody wants to have a look, it's quite interesting, nice argument. He or she can check it easily. Okay, okay. So that's very important. And basically, this result is useful in proving the law of quadratic reciprocities and all. Also, in proving this value, 2p is congruent to minus 1 to the power p square minus 1 by 8 and so on. Okay. So that's what I mentioned, that four cases you will have, and based on this Gauss lemma, it's very easy to prove this result. But most interestingly is this result for the, so there are few more results. I'm not going to the details because they are not within our syllabus, but interesting is the history of proving the law of quadratic reciprocity. I'm just going to show you the history, a brief history about the proof of the law of quadratic reciprocity. So I'm just going to 435. Yes, so here we have this. So this is the Gauss lemma, and this is this, and this is the, okay, yeah. So this is quite interesting. So this is the basically a pictorial proof. So here we are basically counting few numbers on the lattice. So this is the proof of the law of quadratic reciprocity. I'm not going to the proof of this, but I will just give you the basic history for that. That's quite interesting. The history was quite interesting in proving the result. So you now know what is the law of quadratic reciprocity, right? So if you look at, this is quite interesting how the proof actually proceeds. So it was basically mid 70s. Euler, for the first time, Euler, mind that Euler in mid 70s, 1700s, not 70s, uh, he actually found few evidence. So he had some numerical evidence that showed the correctness of law of quadratic reciprocity. But unfortunately, Euler failed to prove this. Later on, so little later on, you can see that in 1785, Ligendre. So after his name, the Ligendre symbol came into play. So Ligendre, for the first time, reformulated Euler's answer, okay, in its modern form. That means the modern form that we have now, like this, okay. But he actually gave several proofs. So Legendre also gave several proofs of the theorem, but each of the proofs contained serious gaps. That means though he formulated the result correctly, but whatever proof that he provided had serious gaps. That means some wrong statement was there. So the statement was correct, but the technique through which he proved that all of the techniques that he gave had some serious gap. The first correct proof was proposed by Gauss. See this Gauss, and you'll be surprised to know that who claimed to have the rediscovered this result at the age of only 18. When Gauss was at the age of 18, he actually rediscovered the proof of, I mean, on his own, he gave the proof of the law of quadratic reciprocity. And Gauss devised 7 more proofs, each based on a different approach. So Gauss actually gave, other than the initial proof, he actually in his lifetime he has given several, even 7, exactly 7 more proofs, and each using different techniques. The proof presented below, so in my book I have given a pictorial proof of this. So that was also given by Gauss, but it actually formally written by Einstein. So he was the, not Einstein, so Eisenstein. So those who have read this Einstein criteria for irreducibility of polynomials, they must know that. So he was a student of Gauss, and he formally written the proof in this pictorial way. So it has a nice history, and we should know about this. But if somebody wants, so this proof is not also very difficult. It's a simple counting techniques, how to count this. And if somebody wants to read this, he or she may go to the PDF page number 338 to get the proof of this law of quadratic reciprocity. Okay. So I'm not going to the details of this proof, but the application is important to us. So proof is not within our syllabus, but when I teach it in master degree level, so they do have the proof of these things, and they have all the proofs that we escaped for the time being for undergraduate level, but for graduate level, for master degree students, they have the detailed proof of this, and there I teach the formal proof. But for you, it's not required. But I'm sure that if somebody is interested, he or she may go to that book, my book in page number something I mentioned already. Okay. So that's the almost end of this part. But now we want to use this results in uh, primality testing. And there, the Legendre symbol will not be sufficient, but based on Legendre symbol, some extra symbols will be required, and that we call Jacobi symbol. Okay. So then the question is, what is Jacobi symbol? So see, Jacobi symbol you can think of is a kind of generalization of Legendre symbol. So what is Jacobi symbol? So here, note that the first change it comes here, it's an odd positive integer. In case of Legendre symbol, this n has to be a odd prime. But here, in case of Jacobi symbol, this n has to be a odd positive integer. Okay. So that's the main generalization of Legendre symbols. So if n is happen to be uh, an odd prime, then this Jacobi symbol and the Legendre symbol will be the same. But in case of Jacobi symbol, we have some generalization of simple being a odd prime. So here n is an odd positive integer. It may be prime, it may not be prime. So it says that, okay, so it says that if n has this factorization, that means the normal factorization that we have in a canonical form, and a be an integer such that GCD of n equal to 1, then Jacobi symbol an is simply defined as an equal to ap, this is nothing but the Legendre symbol, to the power. So here alpha 1, what is this alpha 1? This alpha 1 is nothing but this alpha 1 into ap2 to the power alpha 2 dot dot apk to the power alpha k. Okay, so that is the simple definition. So for example, if I have, say, if I have for example, if I have, say, 100, say, uh, yes, yeah, so if I have, say 7, okay, 700, okay. So you cannot say this is a Legendre symbol because this is not a odd prime, not an odd prime. So this is, so it has to be, sorry, it has to be a odd composite number. So it has to be a, it's a odd positive integer. So it's not 100. So maybe, say, for example, maybe 3 in 3 square into, say, 5, say 45. So I'm little wrong here, so maybe I can replace it, say, okay, so say I want to calculate 45 plus. So as we know that what is 45, 45 is not a prime, but 45 is a odd composite integer, and a here 7 and 45 are relatively prime. So we cannot say this is a Legendre symbol, but suddenly we can say that this is a Jacobi symbol. Okay, okay. So what is then Jacobi symbol? So then write 45 as a product of, so this is 3 square into 5. Then this is value will be 7, 3, and this is alpha square into 7, 5. Now you don't need to calculate anything because it's already squared. So this value, because this is Legendre symbol, both of them are prime. So it becomes 1, and what is this? This is same as 2, 5. Okay. And what is this value? Then this is 2 to the power 2 modulo 5. And this is nothing but minus 1 modulo 5. So this value is nothing one minus 1. So is the idea clear to all of you? The Jacobi symbol. What is that Jacobi symbol?
Yes, sir.
Okay, good. So the Jacobi symbol part is clear. And fortunately, all the properties, that most of the properties that we mentioned about uh, Legendre symbol, here also it holds. For example, if Cn is a odd positive integer and a and b are two integers such that GCD of an equal to 1 and GCD of ab equal to 1, then abn is same as an bn. The proof is exactly the same, so you just distribute it. If a modulo b mod n, then that will imply an equal to bn. A square n is same as 1, 1 n is same as 1, minus 1 is same as this, and not only that, 2n equal to minus 1 to the power n square minus 1 by 8. The same thing that happened in the previous occasions also for Ligender's symbol. So the question is, if we also have the law of quadratic reciprocity like my Ligender's symbol, then we can very easily reduce the whole thing into a very simplified way. So let's check whether we can also have the law of quadratic reciprocity here also, and the law of quadratic reciprocity in this form. So remember, previously we have reduced 1 mod 4 and something like that, but it is in a more general form. So it in this form actually Jacobi symbol or the Legendre symbol was proved. So this is mn into nm, where n and m are two distinct odd positive integers. Then this is same as minus 1 to the power m minus 1 by 2 into n minus 1 by 2. So that is the result. And based on that result, then you can very easily calculate these values. So now if I ask you to do any of the bigger numbers, then you can very easily convert the bigger number into smaller number by using law of quadratic reciprocity when you find that their factorization is achievable. Now see that here we do like this. Now can you using law of quadratic residues, can you convert? So here you know that 45 can be factored in this way, right? So you know the factorization of 45. So for the definition of Jacobi symbol, you should have, if you want to calculate this from the definition in terms of Legendre symbol, then you must know the factorization of 45. But now see, if you don't know the factorization of 45, can you calculate this value? Can you please try to calculate this value 45 without knowing the formal definition of factorization of 45? That means I'm going to use this result. What this result says that mn, so both of them are odd positive integers. So now I can write this 45 7, and that is same as minus 1 to the power 7 minus 1 by 2 into 45 minus 1 by 2. Now calculate this value. What is this value? This is minus 1 to the power 3, and this is minus 1 to the power 44, that means 22, right? So that means this is 1, so this is minus 1. Clear? So what is this value then? So what we want to, this value is easier to calculate because it could be reduced by using this formula. By using this formula, this value could be reduced. So what is this value? So this is basically, if I multiply both sides, so
This should be
745.
plus 1, I think, because minus 1, 22 into 3. So the power is positive. So this should be plus 1, I think.
This is 44, right?
This is 44, 22, and this is 3. So the power of minus 1 is positive. In the we can't write breaking this like
So this is plus 1 and this is minus 1.
we can't break it like this, right? If we look at the previous step, it is coming plus 1 from
Okay,
that.
okay. Sorry. Yes. Yeah, I did a mistake. Yes, you're right. Yes. So it should not be minus 1 to the power. It should be this into 22.
Yes, sir.
Yeah, you are right. Yes. So this is positive. So this is value is 1. Okay. So what is our aim? Our aim is to calculate this value. Okay. So if I multiply both sides by this number 47, sorry, 45, 45 7, 45 7, then this becomes, it was on the right side it was 1, so this is 45 7, right? Now this is basically a whole square. So we know that this value is either +1 or -1, but since this value is whole square, this value will certainly be 1. So 745 is nothing but equal to 45 7, and this value is now very easy. So this is 42, this means 3 7. Now you can very easily calculate what is the value of 3 7. So you can use the simple technique, 3 to the power 7 minus 1 by 2, that means 6. So 7 minus 1, 6 by 2, that means 3 modulo 7. So what is this value?
So -1.
So 27, 28. Yes. So this is -1. So now you see that we can, even without factorizing the value of 45, by using the law of quadratic reciprocity in case of Jacobi symbol, we can reduce this. So that's a very powerful tool. So, and it gives a very efficient way to calculate the quadratic reciprocity without factorizing the value of n. So if we know the factorization of n, then it's really very easy. But even if we don't know the factorization of n, then also we can very easily convert it in terms of law of quadratic reciprocity to get the value of Jacobi symbol. So that's very easy way to calculate this. Okay, is the idea clear to all of you? Is it clear? Okay. So if that is clear, then we are actually going to an application of that. But before that, let us have some idea. So we all know about probability. But in case of probability as well, there are plenty of different things. So sometimes the usually when we go back little earlier, so if we start with this in our normal classes, we when we do the primality testing, what we do, we have some input, some positive integer, and what we want, we check whether the input is a prime or not. So that is known as primality testing. That means I should have as an input some positive integer n, and the output will be to check whether the number is prime or not. Okay. So say my given number say is more than 2 or greater than equal to 2. Then what we'll do, we for the very basic step, what we'll do, we call it, say we start dividing it. Say I runs over 2 to n minus 1. If any of the I will divide n, your conclusion will be the number is not prime. But if none of them will divide n, then your conclusion will be the number is prime. So for example, if I do this problem, say for example n equal to say 10,000, okay, uh, okay, and if I ask you to run this first problem or first algorithm, then you need to run about from 2 to 10,000, right? So 10,000 minus 1, so maybe uh, this many steps. Okay, so one may say that, okay, it may be too difficult for a program to run this many steps. We can have some more efficiency in terms of runtime. Okay, then somebody may say that, okay, I may not go till from 2 to n by 2, but instead I will go up to n by 2. So it was initially n minus 1, sorry, 2 to n minus 1. Instead, I will go from 2 to n by 2. That means some I will vary from 2 to n by 2 means around 5,000. Okay, so it's a quite efficient. See, from here, from around 10,000 to 50,000 around, sorry, 5,000. So from 10,000 to 5,000, that means kind of you gain a step of around 5,000. And somebody may say that, okay, I may do little better. Instead of going from 2 to n by 2 or n minus 1, I will go till square root of n. So I will go from 2 to square root of n. That means 100. That means it will take around 100 steps to do. Now you can see it requires 100 steps around, it requires 5,000 steps, and it requires around 10,000 steps. So if I ask you the question, if I ask you to write a autobiography of a computer on which you are going to run these algorithms, then for that computer, which algorithm it will prefer? So certainly it will prefer the last algorithm. So this is 1, this is 2, and this is, so this is my second algorithm. Sorry, this is my second algorithm, and this is my third algorithm. So among this 1, 2, 3, suddenly the computer will prefer the third algorithm, because in third algorithm it has to run only around 100 steps. But in my first one it has to run around 10,000 steps, whereas in the second one it has to run around 5,000 steps. So in terms of steps, the number of steps that it requires is quite important. Okay, so from here, a term, very important term in terms of theoretical computer science, that known as time complexity. So when I talk about time complexity, suddenly the first thing that comes to your mind, that the algorithm, how much time it takes to calculate, right? So that should be the first thing that one should think when I talk about time complexity. That means you run a mesh program and how much time that it runs for. So you can understand that for the first algorithm, it will take more time than the second algorithm, than the third algorithm. So in terms of time, you may say that, okay, the third algorithm will be the fastest, second algorithm will be the second first, and the last algorithm is the worst among all these three, because it will take the less time, it will take even little more, and it will take certainly the maximum time. Now one thing we are missing, that this time, if we measure the time, then suddenly the time may vary. For example, from machine to machine. For example, suppose I am running the algorithm 1, that means this algorithm, in a very fast computer. For example, say supercomputer. I am running this program. I am running this program in a, say, your laptop. And I am running this program, maybe say the first fourth generation computer. So let's in a very say machine which is around 20 years back. So I am running this program in a machine which is around 20 years back. I am running this program in maybe say my laptop, and I am running this program in a supercomputer. Okay, so I'm running this three algorithms in three different machines, but note that the best algorithm that I am running in the worst machine specification wise, the worst machine that we have. So I have a machine, say maybe say 20 or 30 years back, the machine in which I am running the algorithm 3, which was the best algorithm according to you, and maybe I am running to my current laptop, and this is I am running in a supercomputer. Now with respect to time, then which machine should give you the fastest answer? That means which machine should be the first giving answer machine? So suddenly the supercomputer will suddenly give me the answer, even if I am running with this algorithm 1, which was the worst algorithm among all these three. And suddenly this being quite old specification, so it will certainly take more time to give me the answer. Whereas I am actually uh, calculating, or I have given the algorithm, best algorithm, to the worst machine. So now you understand, if you are going to measure the time in terms of a time that we usually think, then that may not be a good measure, because it depends on machine or machine specification. So that with respect to time means it really not with respect to the time in terms of second, minute or hours. So what do you think that which property of the algorithm remains unchanged? With respect to something, it remains unchanged even if you change the machines. So which property that you think that remains unchanged even if you change the machine? So one part of the algorithm or one part or one specific property of the algorithm that actually remains unchanged even if you change the machine. Anybody can tell me what property?
Sir, number of steps.
Yes. So the number of steps that it requires to complete or finish the work remains unchanged even if you change the machine. So though the time complexity means time, it involves the times, but it not actually in the sense of that time. It actually means how many steps that you are running your program. So based on that, we have the time complexity. So in my first case, the time complexity will certainly be around 9999 or around 10,000. For my second case, my time complexity will be around 5,000, and for my last one, the time complexity is around 100. Now there are many ways to compute the time complexity. So we usually use some order notation. So when you learn about series sequence, mostly sequence, then the convergence rate. So you measured the convergence rate in terms of some symbols like order, big O, small o, etc. So here also we measure the complexity in terms of the number of steps. So the more number of steps required, the it will have more time complexity. So that's why now you have some idea. Now to run these programs, if your computer will have to run this program, then it will have to cover around 10,000 steps. That means it has some time complexity. So this time complexity measure is also an important aspect of theoretical computer science. So measuring how to measure the time complexity, there is another concept known as space complexity. So while you run some program, you might have seen that at your RAM sometimes more pressure comes. So you can measure the pressure at your RAM. That means your RAM is working more. So there are many programs which actually gives more space. Okay. So there is another concept known as space complexity. If your algorithm is said to be efficient if it should have a less space complexity as well as less time complexity. So these two things little bit not exactly independent, but they might have some relation between them, but I'm not going to the details of this, the space complexity and time complexity. So mostly what in our viewpoint, we are basically interested in terms of time complexity, because nowadays we have lots of memories. So memory is not that issue, but the issue is how efficient is your algorithm. If your algorithm takes lesser step, then we call it this is a good algorithm. For example, here it takes around the order, if you write in terms of order of n, okay, here it takes order of around n by 2, though this order in terms of order this is same as n, and this is taking order square root of n. Okay, so certainly this will be the best algorithm among this. But unfortunately, if your number is this big, then if you consider the square root of n, then it would be around half of this steps. So it has around 904 digits. So maybe the square root will contain around 450 digits. But still, if the number is this big, then for supercomputer also, this many steps, then the supercomputer has to run. And unfortunately, for supercomputer also to run this many steps, it may take more than maybe the age of the universe, or maybe say at least 100 years. 100 years is nothing to run this. but suddenly it will take a lot of time. As a result, you cannot use this algorithm for your primality testing. Usually, how to calculate whether this number is prime or not. So this big number. But there are some efficient algorithm which can give you the answer quickly. That means in a very efficient way. So usually efficient algorithm means polynomial time algorithm. So I'm not going to details of it. If somebody is interested to check the time complexity and the order notation, then he or she may go to my book at the page. I forget this page number, but chapter 10, there is a one section is there on which I have explained in detail in a simple with simple examples what this time complexity means and how to measure this and what are the notations that are used for measuring this time complexity. But in my class, because it's not required at this moment of time, but for master degree students, I usually teach them. But for your syllabus, it's may not be that required. But still, it's good to know all those things. Okay. So now I come to how to get an efficient algorithm to check whether a number is prime or not, and the number should be of this big number. So to understand that, we need to have some probabilistic algorithm. See, the algorithm that I just now I have shown you, they are all deterministic algorithm. What does it mean? Deterministic algorithm mean if you give a number, it will certainly give you an answer. You may not know after how many years or how many days it will give you, but it will certainly give you an answer, and that answer must be correct. That means either it will say you the number is prime or the number is not prime. That means the deterministically they will give you the answer. But to get efficiency, to achieve efficiency, we consider another type of algorithms which we call it probabilistic algorithm. That means if you ask him a question with some probability, it will give you the answer. For example, if I ask you a question, you must say either that is yes or no. And if I say that, okay, if you say yes, then suddenly the answer would be correct. And if you say no, then the answer may not be correct. That means there might be some chance or possibility of giving me wrong answer when you say no to me. But if I assume that when you say yes to me, then suddenly you have given a correct answer. Okay. So that is known as yes-biased Monte Carlo algorithm. So firstly, for a decision problem. So what is the meaning of decision problem? Decision problem means you have to give me answer in yes or no, nothing else. That means in a binary mode answer. So your answer will be either yes or no. It's not like a long answer type question. So you don't have to explain things. You have to just give me the answer in yes or no. So that we call it decision problem. So for a decision problem, a yes biased Monte Carlo algorithm is a randomized algorithm in which yes answer is always correct. That's why it's known as yes biased, but no answer may not be correct. Okay, that's what I tell you. Not correct means you have a probability through which you can measure. That means you might have some wrong, you may get a wrong, no answer, but if you know that with how much probability that you are getting the no answer correctly, then you are basically done. So that's why, but in one stage, that means if you get the yes answer, then suddenly you are done. Similarly, for a decision problem, a no-biased Monte Carlo algorithm is a randomized algorithm in which a no answer is always correct, but a yes answer may not be correct. Okay, so if you have a yes-biased Monte Carlo algorithm, then if you get an yes answer, then you are done basically. But if you know the answer is no, then there might be some chance that you may get a wrong answer saying that it's no. But if you have by some means, if you can have some bound on the error, that means you might have some error while you get the no answer. But if you have by means some chance that you can reduce the error probability, then you are basically done. So that is known as something. So for a decision problem, a yes bias Monte Carlo algorithm has an error probability epsilon if for any instance the answer is yes, but the algorithm will give you an incorrect answer no with probability at most epsilon, where the probability is taken over all random choices made by the algorithm when it run with a given input. So when it gives you a wrong answer, when, so suppose you have an yes biased Monte Carlo algorithm, that means when you are getting yes, you are already done. Okay, now we need to check what's about no. Okay, so you get no answer. Now think about when you get a no answer and when you think that the no answer is a wrong answer, then what should be your correct answer? The correct answer should be yes, but by mistaken it has given you a answer no. That may happen in case of no, but if your algorithm is has some error probability epsilon, then you have made your algorithm in such a way that even if it gives you a wrong answer when it says no, then also the error probability of your no answer should be bounded by epsilon. Then we say that a yes biased Monte Carlo algorithm has an error probability epsilon. Is it clear to all of you? Is it clear?
Sir, no, sir. Please repeat the second definition.
Okay. So suppose you have yes biased Monte Carlo algorithm. So suppose this is an algorithm. So this is a decision problem. So you have some input and I am considering yes biased. So it either say yes or it say no, right? According to the definition, if it is yes, then it is always correct. That means the probability of error in case of yes is 0. Okay. Now there might be some mistake here. That means I give you say some input and your algorithm give me an answer no. Then I cannot say directly that that number is the no answer is correct. For example, suppose this is an algorithm for primality checking, say PC, primality checking algorithm. I have given him some input n. Okay, and I ask him the question, is it composite? Is it composite? Okay, now so mind that my target is to check primality testing. So I may ask him another question, is it prime? But here I have asked him the question, is it composite? So I have given him n and I am asking him the question, is n composite? So if it says yes, so as I mentioned, it's my yes biased Monte Carlo algorithm. So if it gives you the answer yes, then what will be your conclusion? The suddenly n is a composite number. That means n is not prime. If it is a composite number, it cannot be prime, right? But if it gives you the answer no, that means it is not a composite number. That means it is a prime number. If this algorithm gives you the answer that no, it is a prime number, then there might be some question of doubt. So you may not accept it correctly, because when it says you no, there must be a problem that it may give you a wrong answer. So what is his answer? No. That means the number is prime. The number is prime. The number is prime. So when it will give you a wrong answer, the number is prime means the number is actually composite, but by mistaken the algorithm gives you the number is prime. That's the error. So the number n is actually composite, but by mistaken your algorithm gives you no, the number is not composite. That means the number is prime. But if you have some confidence in terms of probability, that means if I can say you that the probability n is so that is the error probability. What is the error probability? The number n is composite, so that is the error. Given that, so it
Sir, we
should be a
can
it, yes.
sir, we can see this as a hypothesis testing, like type 1 error, type 2 error.
Yes, exactly. Type 1 error or type 2 error, but you can think this is, yes, the same thing. The conditional probability. So the answer is no, but the number is composite. So the probability that the number is composite, but the condition is given that the number is prime. This probability should be, so this is the conditional probability, the number is prime, this probability should be less than epsilon. That is the meaning of the error probability. Is it clear? So I'm writing it, so this is little messy here, so I'm writing once again. So what is that error? So probability that number is composite, but given that number is prime. So this is the error. This error should be less than epsilon. That means you have bounded the error. The error cannot be that. So what you want, this error you want to be minimized. So if this error is minimized, then basically you are done. Because for yes biased case, for yes you are always correct. For no, you have a very less chance of getting wrong answer. Then you are done basically. So that's why this Monte Carlo algorithms are very important. Now is it clear?
Yes, sir.
Okay, so when I will show you the example, then it will be even little more clear. Okay, so what is our aim? Our aim is to basically check whether a number is prime or not. Mind that here I may also ask the same question like this. I may ask the same question to my algorithm: is the number prime? So this is my question, and here you have n. So here also you will have two answers, yes or no. I may have the same problem by asking the question, is the number composite? And I will have again same yes or no with the same input n. But essentially these two statements are different. One is both of them I want yes biased, right? So in case of testing this, is the number prime? If it gives you yes, that means when you get a prime number, yes, when it gives you yes, then suddenly the number is prime. Here, when it says yes, then the number is suddenly not prime. That means composite. Here yes means prime, and here yes means composite. Okay, but the same thing, but the question is different, and depending on both of them are yes biased. So in case of the first problem, that means is the number prime, if it gives you yes, then your conclusion will be suddenly prime. And in the next problem, next statement, is the number composite, if it is give you yes, then your number is suddenly composite. But both of them will do the same thing, but I have a twist here, and then you can understand why I am not considering this one, but I am considering this one. Because law of quadratic residues or quadratic residues will help me to have to get my correct answer using this question. So here my question is composite. So instance is a positive integer n greater than, so instance means input, and question is composite. So is n composite? So it's a decision problem. So is n composite? Your answer will be either yes or no. Now let me check how to handle this problem using quadratic residues. The idea is very simple. Okay. So before that, before going to that question, I'll just first write it down a bit. Okay. So maybe I can erase it. Okay. So idea is like this. So as I mentioned earlier, if P is odd, P is an odd prime, or remove this if P is an odd prime and GCD AP equal to 1 will imply AP convergent to a to the power P minus 1 by 2 modulo P, right? So we have already seen this result. So instead of, okay, another thing is that this Ligendre symbol value AP. Okay. So here I need to calculate two things. If P is prime, then this happens. Now, if by any chance, if you have this conclusion, so if you found this, where you don't know, whether you have no idea whether P is prime or not, but you know that AP, that means you start with, say, this is Jacobi symbol, and you found that this happens, what will be your conclusion? What will be your conclusion? So you calculated as a Jacobi symbol. I have given you A and P. You have no idea whether P is prime or not, but you know that GCD of AP equal to 1. So P is a odd number, and then you can calculate the Jacobi symbol efficiently by using law of quadratic reciprocity, and then you can calculate this one also by using square and multiply algorithm. As I have already mentioned while I was teaching you the RSA crypto system, that a to the power P minus 1 modulo P can be very easily calculated, efficiently calculated by using law square and multiply algorithm. So you calculated this part separately and this part separately. Okay, and you found that these two values are not equal. Then what will be your conclusion? Can somebody tell me what would be your conclusion?
Sir, A is not residue.
See, it's when you residue concept comes into play when
Sir, and you can say that P is not prime or GCD of A and P is not equal to 1.
no, here we have taken GCD of AP equal to 1, we have already taken. So this part, in this part, we have already checked GCD of AP equal to 1, and then we calculated this, because when you are going to calculate Legender's Jacobi symbol, you need to check this first. Unless they are equal to 1, you cannot calculate Legendre Jacobi symbol. So according to the definition, GCD of AP should be equal to 1 in case of Legendre Jacobi symbol. So when you calculated this, at that time you have already checked whether this is value is equal to 1 or not. So then what would be your conclusion? Is the question clear? So you have already
Then
calculated,
I can say that P is composite,
yes. So
because if
that,
P is prime, then we can have this by using
yes.
the symbol.
So that will imply P is composite. Now, it may be little difficult for you to understand this, but when I write in a logical sense, as I already mentioned, A implies B is logically equivalent to negation B implies negation A. See, what was my statement here? P odd prime and GCD AP equal to 1 will imply this, right? Will imply this. So in case of P odd prime, the Jacobi symbol and Ligendre symbol are the same. So if P is an odd prime, and suppose we have already checked this one, because in case of calculating the Ligendre symbol or Jacobi symbol, this has to be equal to 1 GCD. So you are calculating if P is an odd prime and GCD AP equal to 1, suddenly this equality holds. Now what is in terms of negation? So if you consider this to be A and this to be B, don't consider this one. So already I have GCD AP equal to 1. So statement A is P is an odd prime and it's already given. Don't consider this to be A. Then that will imply the equality, the statement B. Now what is the logical equivalent of this? Negation B should imply negation of A. What is negation B? Negation B is nothing but not equal, not equal, negation B. And then what is negation A? Negation A is P is an odd prime. That means P is a composite integer, because if I assume that P is the n here is always a odd integer, so here if we consider this to be an odd integer, see what we want to check here is to check whether the number is prime or not. Suddenly if you want to check whether the number is prime or not, then the first thing you should check whether the number is even or not. If it is even and if it is not equal to 2, then suddenly your conclusion will be the number is even, as a result it's not composite. So whatever we are going to give as an input, it has to be a odd number and it has to be more than 1, even more than 2. So this part is also done. That means if we have negation A, that means P is an odd prime number, and that means it has to be a composite number. Is it clear? So now this negation B implies negation A will reveal you that if this does not hold, this equality does not hold, then suddenly your conclusion will be the number P here, what will be the input here, is not a composite number. That means that will be a prime number. Again, mind that I am going to show you this is a Monte Carlo algorithm. That means if it says yes, then suddenly your answer is correct. But if it says no, then suddenly the answer may not be correct. It will have some probability of error that we have to calculate how much probability that you might have. Okay, so let's check what is the algorithm. So here input would be some odd integer. Suddenly for you are going to check for n is prime or not, and that should be for big numbers. So for big numbers n has to be odd, right, to check whether the number is prime or not. So an odd number which is strictly greater than equal to or greater than equal to 3. Now choose an integer randomly from 2 to n minus 1 and check the GCD. Again, for big numbers also, in my previous classes, while teaching you the RSA encryption, we mentioned that Euclid algorithm is very efficient to calculate GCD. So even if for big numbers, the GCD calculation is very easy. So choose a random integer a between this and this, and then check whether a and n GCD is 1 or not. If the GCD is 1, sorry, not equal to 1, then what would be your conclusion? So you have given some n which is strictly greater than equal to 3, and you found some a which is less than equal to n minus 1. It's not even n. So GCD of an from taken a has been taken from 2 to n minus 1, and you found that the GCD is not equal to 1, then suddenly your conclusion will be the number n is a composite integer because it has a common divisor. Okay. So now you have checked the position that your a and n, if it passes this, that means if it comes here, that means GCD of an is not equal to 1. Okay. Sorry, equal to 1. So if it comes here, if it return means the program will output this and it will be terminated. Return in that sense. In computer science, when we put return, it means after giving this result, the program will be terminated. That means it will not come further. So if it will come further, that means that step did not happen. As a result, when it comes here, it means GCD of an is must be 1. As a result, you can calculate the Jacobi symbol because n is a odd integer and a and n GCD is 1. So you can calculate this Jacobi symbol. Now you can also calculate, so as I mentioned, by using a quadratic law of quadratic reciprocity, you can certainly calculate the Jacobi symbol. Now you can also calculate this part by using square and multiply algorithm very efficiently. So now you have x and y. Now if x is congruent to y, then your conclusion is no. But if x not equal to y, that means in else part, then your conclusion is yes. The number is composite. See, just now I have mentioned if they are not equal, then you are confirmed that the number is composite, right? But if they are equal, then you may not be sure, but you have to give some answer because it's a either yes or no answer you have to put. So that's why you put no, but you might have some doubt that when I put no, that means when I say that the number is prime integer, then suddenly there might be some wrong answer. That means the number may be a composite integer, but using this algorithm it gives you the answer no. That means the number is prime integer. That means the originally the number is even composite integer, but your algorithm gives you the no answer. So we need to check how is the error. Okay, so till now is it clear to you? Is the algorithm clear to you?
Yes, sir.
See where it gives you the yes answer. When it gives you the yes answer, then suddenly the number is a composite integer. There is no doubt about that. When it gives you the yes answer, suddenly the number is a composite integer because this does not hold. And if it does not hold, then negation B implies negation A implies basically A implies B, or other way around, A implies B is equivalent to negation B implies negation A. So here you can consider this to be, is it clear to you now? AB from A and B, what is A and what is B? So A implies B, and if you found this, that means if you found negation B implies negation A, that will certainly imply A implies B. Is it clear? Or shall I repeat in terms of other way? Okay, I will just again repeat once again. It may be little confusing to you. So what you found say given given n and a, what you calculate an. Okay, so the GCD is 1 already, I have checked it. If they are not equal to 1, then we are done basically. Now we are checking the case when their GCD is 1. So calculate this and then calculate a to the power n minus 1 by 2 modulo n. Okay, and check whether they are equal or not. If they are not equal, okay, then what will be your conclusion? That we want to check. Okay, so suppose in my Ligendre symbol case, what we have written? So A is such that GCD of an equal to 1, then n is, so n is odd, so n is prime, that will imply a n should be equal to a to the power n minus 1 by 2 modulo n. That we have already proved in my last class. In today's class we have also revised this. So if this is prime, that will imply this. So what would be the negation of this? If this not happens, an not equal to a to the power n minus 1 by 2 modulo n will not happen, that will imply negation of this. That means n is composite. Now I think it's clear. So if this happens, then suddenly we will be able to say that there is no doubt here that n is composite if they are not same, because these conditions are already happened, already checked. For that, if this happens, this portion happens, then suddenly your answer will be n is composite. So that's why when we say yes, here we say that yes, when they are not equal, if they are equal, we may have some doubt. But if it says yes, when it says yes, else part, else means when they are not equal, when x is not equal to y modulo n, then we have yes, and yes means it will give you the correct answer. Clear? So now the question is, what would be the probability of saying the wrong answer? And I'm not going to the proof of it. If somebody wants to check the proof, it's already I have done in details in my book, so one may refer to that. And it has been shown that the Solovay Strassen Primality Testing algorithm is a yes-biased Monte Carlo algorithm with error at most half. What does it mean? That means if it says you the answer no, then the probability of error will be at most half. So you may think that okay, half is a quite big number. So with probability half, you can always say that okay, the number is prime or the number is not prime. So you can make a coin toss, and whatever, say if you say that if head comes, I will say prime, and if tail comes, I will say not prime. Then the probability of error will also be half there. Then what is the big deal about it? Here, the idea is, here I have given only for one run. So here I have taken a randomly from this. Suppose it gives you an answer no. Okay. Then the probability of error is half. Then you again with the same n run the program with again randomly chosen from this. So you may take another random a from this interval and again run the same program. So it may happen that it gives you again the answer no. Now after two runs, what is the your error probability? Can you tell me? After two
So
runs, what is your error probability?
1 by 4.
Yes, it's 1 by 4 because A is randomly chosen. Second time, the event is independent of the first time. So the error probability, because you know that the previously the answer was no, and then you are again doing this with the same n but with a randomly chosen A, and you again get the answer no, then if you are not satisfied, then again run the program. And if you again get the no answer, then the probability of error after 3 runs will be 1 by 8 and so on. So after 100 runs, the probability of error, and if at every stage you get the no answer, then the probability of error would be half to the power 100, which is almost zero. So you can reduce it, and if you are not sure about it, then run again, maybe 1 lakh times, because they are very efficient. You can very easily run the whole program 1 lakh times, and then you will get every time if you get no, then your probability of error after 1 lakh times will be half to the power 1 lakhs. So you can understand how many zeros will be there just after point. So that is more practical, and for more practical purposes, this is the process. So there are few probabilistic algorithm tests are there, which actually when we run the program, for example, when we apply the thing in case of say here, so this is Solovay Strassen algorithm. Say I have given n equal to, say, maybe I can print it like here, print say n, then see this is my n, okay, and I'm going to check whether the number is prime or not. So here you can see that I have given a counter. That means I am actually testing it for 10 times, and for all the 10 times I get the same answer no, and after 10 times I will return if every stage I get the answer no. In between it, at any stage it gives you the answer yes, then suddenly the number is composite. But in all the 10 occurrences, it gives me the answer no, 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 no. As a result, after 10 runs, I will declare that the number is prime, but since it's a yes bias, there might be a error. Probability of that error will be bounded by half to the power 10. That means 1 by 2014. The probability of error. So if you are not satisfied with 100, then make it 20 runs. And then you can see that at every, so the number is fixed, and at every trial, this means that at every trial, if you declare the number is prime, when it gives you the answer no, that means there might be half to the power 20. That means almost zero. And see how quickly it gives you for such a big number. So you may think that okay, this is may not be quite big to you. So this is 2 to the power 100. So next prime to the 2 to the power 100. So maybe next prime 2 to the power 1000, and I am satisfied with say 10 numbers. So I will run the program for 10 times, and the next prime, which is just after 2 to the power 1000, let me check. It will take some time, that you can understand. I am checking it for 10 times, the same thing, and after some time it will give me the answer that what is my prime. And so this is my prime number. Now you can see that how big it is. It will have around 300 digit many times, and all the 10 times it gives you no answer. And at the end of this 10 steps, it gives me the answer that the number is prime, and we say that this number is okay. So maybe we can put some extra odd number, okay, maybe 2 to the power, okay, so not here, maybe 2 to the power 500 plus say 1. Let's check. So the number is 2 to the power 1000 plus 2 to the power 500 plus 1, and let me check whether the number is prime or not. So it will take some time. So you can see that the green marks means it's working. So the number is this, and oh, that is also a prime. Okay. Oh, so it has to be a prime because I have taken next prime of this. Okay, so it will be next prime of this. But instead, next prime, let me check with this number. The number is this. And see, it gives you readily that this number is composite. That means it gets some value A for which this equality does not hold. As a result, it will readily give you with a full confidence that the number is composite. See how quickly it gives you. Okay, can you give me some other number if you wish? You can add here. So I may make it, if I increase it a bit, and sometimes it goes here and there. Okay, now it is easier for you to see. Let's see. Okay, do you want to insert some other number? Some other number, anybody? Maybe let's check with 600. Oh, it also gives you very quickly. See, you can understand how many steps it takes. It just one step. Instantly it gives you the answer. Maybe some smaller, maybe I put it 101 for a test. Oh, it's also a composite. Any number you want to put here? Then we can check. So now you can understand how quickly it can generate. And I have the digit 900 digit long, so that prime is somewhere here maybe. Anyway, so it will take some little bit more time to, yes, so this is the number. So that I printed here is this number. So this is the next prime of 2 to the power this. So Sage also itself, it also uses this probabilistic algorithm to find this. So I have written this code for Solovay Strassen. There are another, that is Miller-Rabin. Solovay Strassen. There is another algorithm called Miller-Rabin, which we also have in our syllabus. So this is the Solovay Strassen, and yeah. So that's all. So any question you have?